Now, we're going to take up the shear force, bending moment, and axial force. First, we're going to take up the shear force. The shear force SF at any section of a beam is equal to the algebraic sum of the vertical forces, that is, forces perpendicular to the axis of the beam, to the right or left of the section. So that means the load algebraic sum of vertical forces, that is forces perpendicular to the axis of the beam, that is the load which is coming on the beam, is the shear force. What is bending moment? The bending moment at any section of a beam is equal to algebraic sum of the moments of all the forces either to the left or the right of the section about the section is the bending moment. Then the axial force. The axial force at any section of a beam is equal to the algebraic sum of the forces parallel to the axis of the beam, either to the left or the right of the section. So in the shear force, that is the vertical force what is coming, and the bending moment, the algebraic sum of moments, and in the axial force, the horizontal force which is coming on the beam. Next, we will going to take up the maximum bending moment. So the rate of change of shear force is equal to the intensity of load, that is dF by dx will be equal to W. Similarly, the rate of change of bending moment is equal to the shear force at that section. That is, for maximum bending moment, dm by dx should be equal to 0. That is, Bm is maximum when shear force is equal to 0. But practically, the bending moment will be maximum where the shear force changes its sign. That is, at a point where SF will change the sign from positive to negative or vice versa. So, and bending moment is maximum at that particular point. So, these things will going to be discussed in detail when we're going to take up the problems. And the relation between the load, the shear force, and the bending moment. Suppose if we are considering the cross section of the beam, wherein we have the intensity of loading of W per unit length, wherein the uniformly distributed load over a section. So then we have the forces which is acting upward direction on the left end of the beam and the clockwise couple M, and then we have the cross section which is delta X. Then W per unit length is the load which is acting downwards from the top, and F plus DF towards the right hand downward direction, and counterclockwise couple at M plus delta M, which is on the right hand. Let capital F be the shear force at the left hand face of the element. F left dF, F plus delta F is the shear force at the right hand face element. Then capital M is the bending moment at the left hand face of the element, and M plus delta M is the bending moment at the right hand face of the element. And W is the mean rate of loading or mean load intensity of the length delta X. And W into delta X is the total load on the elemental length, which is delta X. And for equilibrium, sigma F and sigma M will be equal to 0. So that means algebraic sum of forces and algebraic sum of moments will be equal to 0. So first we are going to take up the shear force. For the equilibrium of the elemental length, so what is that? Sigma F will be equal to 0. Calculation from the left end if you are considering. So that means the load which is acting upwards from the left end is considered to be the positive value. Therefore, F minus W into delta X, because the load is acting from the top towards the downward direction, and minus F in minus of F plus delta F is the load which is acting on the downward direction towards the right end is equal to 0, because we say algebraic sum of all the forces should be equal to 0. So that means here if you are considering F is acting towards the upward direction, calculation from the left, which is positive, F minus we have W into delta X, which is acting from the top towards the downward direction, and also the force which is acting downward, F minus of F plus delta F. So that is from calculation from the left towards the right. So when you are considering that, so you will going to get this. So when you expand this, minus W into delta X minus delta F will be equal to 0, because when you open the bracket, F plus F and minus F will going to get cancels, and transferring that delta F towards the right side, minus W into delta X will be equal to delta F. Therefore, delta F by delta X will be equal to minus W. As delta X is tends to 0, dF by dx will be equal to minus W, where small w is the mean rate of loading or mean load intensity of the length delta x. W into delta x will be total length or total load on the elemental length delta x. For equilibrium, sigma f and sigma m will be equal to 0. Now we are going to consider the shear force. So we have considered about the equilibrium. So for the equilibrium of the elemental length, sigma f will be equal to 0. So again we have the same equation. So that is minus w into delta x minus delta f will be equal to 0. So delta f by delta x will be equal to minus w. As delta x tends to 0, df by dx will be equal to minus w. So thus the rate of change of shear force at any point on the axis of the beam is equal to the intensity of the distributed load at that same point. Based on the direction of loading, the intensity of the load, that is W, will be either the positive or the negative. If there is no distributed load on a segment of the beam, then W will be equal to 0. That means if you are not considering the distributed load, then W will be equal to 0. Then dF by dx will be equal to 0. So SF is constant, then dF by dx will be equal to constant, and the SF varies linearly in that segment of the beam. So this will going to be discussed in detail with the examples when we take up the problems. So next we are going to take up the bending moment. For the equilibrium of the elemental length, sigma m will be equal to 0. That is, the algebraic sum of the moments will be equal to 0. Calculation from the left end, that is clockwise moment, m plus f into delta x minus w into delta x by 2 minus counterclockwise moment, which is minus m plus minus of m plus delta m will be equal to 0. So once you are considering that here, then it will be f into delta x will be equal to f into delta x minus delta m will be equal to 0. As the delta x itself is small, delta x by 2 is further small, so then automatically that will going to be neglected. So delta m will be equal to f into delta x. Therefore delta m by delta x will be equal to capital F. As delta x tends to 0, dm by dx will be equal to f. So thus the rate of change of bending moment at any point on the axis of the beam is equal to the shear force at that same point. So maximum value of bending moment is obtained when dm by dx will be equal to 0. This is also the condition for the minimum value. Therefore, has a maximum value when the SF is 0 or changes its sign. So that means when the shear force changes its sign at that particular point, we will going to have the maximum bending moment. So from the equation, dF by dx will be equal to minus W. So dF will be equal to minus W into dx. Integrating between the limits of the 2 points between capital A and capital B. So integration of dF will be a to b will be equal to minus integral of a to b into w. So that will be equal to fb minus fa will be equal to minus of integral of a to b w into delta x. Fb minus fa will be equal to change in the shear force between fa and capital B. So integral of a to b w into delta x will be equal to area below the load diagram between A and B. it is equal to the magnitude of the resultant of the distributed load acting between the points capital A and capital B. So thus the change in shear force between 2 points along the axis of the beam is equal to the total load downward between those 2 points. So that means from equation dm by dx is equal to F. Dm will be equal to F into dx. So integral of dm between the limits a to b will be equal to taking the integral on both the sides. Integral of a to b F into dx. mb minus ma will be equal to integral of a to b F into dx. So you call this equation as 1. So mb minus ma will be equal to change in the bending moment between a and b. So integral of e to b F into dx will be equal to area below the shear force diagram between a and b. So from equation 1 is valid even when concentrated load acts on the beam between 2 points capital A and B. And number 3, however, it is not valid if a couple acts between A and B. A couple produces a sudden change in the bending moment at the point of application of couple. And the point number 4, the shear force does not change at the point of application of couple. And number 5, an abrupt change or sudden change in the shear force occurs at any point where a concentrated load acts. So this is how you will be able to discuss about the different types of forces, which is the shear force, the bending moment, and the axial force on the beam. Thank you.